This is the Instrumental Methods of Analysis course review on spectroscopy. Remembering that we first start with the properties of light because in spectroscopy we are measuring at least one of the different properties of light. We start with nu times lambda, giving us C, where nu is the frequency, lambda is the wavelength, and C is the speed of light. So with frequency, or nu, we're looking at how often or how fast a given wave passes a fixed point in time. Lambda is the length of the wave, or the distance between equivalent points on adjacent wavelengths. So from the top of the peak to the next top of the peak would be a wavelength. We also have energy equals h nu, where h is Planck's constant, and again nu is the frequency of that electromagnetic radiation. By combining these first two equations, we can also get the derivative, where E equals hc over lambda, or Planck's constant times the speed of light over the wavelength. And in that last equation we see hc times nu bar. And again, nu bar is the wave number, and that's what we typically use in infrared spectroscopy, and it is the reciprocal of the frequency. This, as a reminder, is the whole electromagnetic spectrum. In spectroscopy we are looking at radiation somewhere along this electromagnetic spectrum. In microwave, the electromagnetic radiation has enough energy to cause rotation of the molecules. In vibrational spectroscopy, we are looking at infrared radiation and in those frequencies. So with infrared spectroscopy, we're only looking at vibrational modes for a molecule. In ultraviolet and invisible, not invisible, but visible spectroscopy, we're looking at colored solutions, generally for the visible area. And ultraviolet, these are electronic excitations, so we're, by the absorption of that energy of electromagnetic radiation, we're causing electrons to jump to different levels. Or if we're looking at emission spectroscopy, then we're looking at the electrons dropping down from excited levels to the ground state. When we get at higher energies than this in X-ray and in gamma rays, then we have energy to actually break the bonds and ionize the molecules. Most of the quantities that we're measuring are related in some manner to either transmittance or absorbance, where transmittance is power over initial power. So if we have the power of the electromagnetic radiation that's initially coming through the sample, or that's initially being generated by the instrument, when it hits the sample, if it absorbs some of that radiation, then the amount of power that is transmitted through the sample is reduced. So P over P0 is going to be something less than 1. You're going to see a transmitted power that is less than whatever that original power is in the denominator. That's related to the absorbance on a log scale, where absorbance is the negative log of the transmittance and is related to the amount of energy that's absorbed by a sample. When we look at Beer's law, we're taking into account the absorbance of a solution, where in this case the absorbance equals ABC, where A is the molar absorptivity, B is the cell path length, which is generally the width of the cuvette, and in most standard spectrometers that we use that's 1 centimeter, and C is the concentration. We use that to calibrate an instrument, meaning that we run a calibration curve, or we analyze several different concentrations of our analyte. Absorbance should be a straight line relationship, so we should be able to get a straight line of the Beer's law curve, where we're plotting absorbance on the y-axis, concentration on the x-axis, and the slope of that line is the absorptivity times B. Once we have this calibration curve, then we can use that relationship in order to analyze unknown samples, and we can plug the absorbance of our unknown sample into that straight line curve equation and calculate C, or the concentration of the unknown. Keep in mind too that the absorbance of a solution is the additive absorbance of all of the individual components. So if your solution is a mixture of several different components, then at any given wavelength, the absorbance of each one of those components is added together to get the measured absorbance for the solution. In infrared, again, we're looking at vibrational modes. When a molecule picks up or absorbs infrared radiation, it can cause the molecule to vibrate. That has to do with whether or not the molecule experiences a change in polarity with that vibrational mode. We define several different modes. In a symmetric stretch, the bonds are lengthening and contracting at the same time. So if you have a molecule that is symmetrical, during asymmetric stretch, the dipole moment does not change. In asymmetric stretching, some of the bonds may be expanding while other bonds are contracting. In bending, you see the bend around the angle and the bond angle slightly changing, and there are several different modes of that bending vibration. It's not always possible in infrared spectrometry to assign a given vibrational mode to each peak in an infrared spectrum, so in many cases every peak in the spectrum may not be assigned. In absorption and emission spectra, we're looking at the promotion of an electron from a ground state to a higher level energy state. Because those energy levels are consistent in a given molecule, the absorption and the emission spectra occur at the same energies. So you see the same wavelengths of light in absorption or emission, because either the molecule is absorbing that wavelength of light in order to excite the electrons, or it is emitting that same wavelength of light when the electron drops back from the higher energy level to the lower energy levels. And that is the end of the review on spectrometry.